All right, welcome back, focused learners. Today's explainer tackles one of the most foundational and, let's be honest, sometimes completely misunderstood concepts in physical chemistry. We're talking about Raoult's law. If you've ever stared at the dense thermodynamics textbook and just wondered how invisible, microscopic molecules dictate the real-world properties of the liquids we use every single day, well, you are exactly in the right place. We're going to build your mental model layer by layer in a really focused, step-by-step breakdown. Because by the end of this, we aren't just going to blindly memorize equations, right? We're going to genuinely, intuitively understand them.
Okay, let's dive into this. Have you ever wondered why tossing a handful of salt into a pot of water actually changes how it boils? Or why mixing two totally normal liquids together creates a solution that acts, well, completely differently than either of the original ingredients? That's the core mystery we're solving today. Why does mixing things together fundamentally alter their physical properties, specifically their vapor pressure? It all comes down to the microscopic, borderline chaotic behavior of molecules. And that is exactly what Raoult's law explains for us.
So here is our roadmap for today. We'll start with what exactly is Raoult's law? Then the actual science of vapor pressure. Next, understanding ideal solutions, followed by real solutions and their deviations. And finally, the impact on colligative properties. Let's get right into it.
Section 1. What is Raoult's law? Let's lock down that core thermodynamic principle. Picture this. The year is 1887. A French chemist named François-Marie Raoult is hard at work in his lab. He's meticulously observing what happens when different random substances get mixed together into a solution. And through all this rigorous testing, he noticed a super consistent phenomenon. Literally every time he mixed a solute into a pure solvent, the vapor pressure of that whole solution decreased. Every time. It wasn't just random chance. It was a highly predictable, mathematically perfect thermodynamic relationship.
And out of all those meticulous observations came this formal definition. It states that a solvent's partial vapor pressure in an ideal solution is equal to the pure solvent's vapor pressure multiplied by its mole fraction. Now, okay, I know, that sounds like a total mouthful of chemistry jargon, but don't stress. We are going to break down exactly what that actually means in plain English, and I promise you, by the time we hit the math section, this definition is going to feel like second nature.
Moving on to Section 2, the science of vapor pressure. Before we crunch any numbers, we've got to visualize the physical mechanisms at play.
Now, what's really interesting here is the concept of dynamic equilibrium. It's fascinating. Just imagine a tightly sealed jar, and inside there's just pure water. Now, at any given temperature, some of those liquid water molecules get pumped up with enough energy to actually break away from the surface and evaporate into a vapor. But at the exact same time, some of those vapor molecules are crashing back down into the liquid surface and condensing. When the rate of that evaporation perfectly matches the rate of condensation, boom, we hit this sweet spot called dynamic equilibrium. And the pressure exerted by that vapor onto the liquid at that exact balanced moment, that's the pure vapor pressure of the substance.
So what happens when we mess with that perfect pure liquid by, say, dumping in a solute, like a powder? Paint a mental picture with me here. You add these new solute particles into the solvent, they mix in, they fill up the gaps between the solvent molecules, but crucially, they take up actual physical real estate right on the very surface of the liquid. Because you now have these blocking solute particles hogging the surface, there's literally less surface area for the original solvent molecules to escape into the gas phase. The vapor molecules can still condense back down easily enough, but the evaporation part is physically hindered. The inescapable result? The total vapor pressure of the solution absolutely drops. All right, Section 3, Understanding Ideal Solutions. Let's quantify this and look at the mathematical formulas and variables. When you're mapping this out for an exam, you basically have three core variables to track. First, P solution. This is the new lowered vapor pressure of your entire mixed-up solution. Next, X solvent. That's the mole fraction of your solvent. Basically, what percentage of the total molecules in that liquid actually belong to the solvent. And finally, P not solvent. That's the one with the little zero superscript. That represents the original vapor pressure of the solvent back when it was perfectly pure, before we added anything to it.
Smash them together and you get Raoult's equation. The new vapor pressure simply equals the mole fraction of the solvent times the pure vapor pressure. It's a direct, purely proportional relationship. So think about it. If your solution is 90% water molecules, meaning a mole fraction of 0.9, the new vapor pressure is literally just going to be 90% of pure water's vapor pressure. As the mole fraction of the solvent drops, because you're adding more and more solute into the mix, the vapor pressure just drops right along with it. Make sense?
But wait, what if the thing you're adding to your solvent is also a liquid that loves to evaporate? Like say we're mixing liquid A and liquid B together. In this scenario, both components are what we call volatile. They both desperately want to escape into the gas phase, so they both exert their own partial pressure. This is where it gets cool. Here, Raoult's law seamlessly teams up with Dalton's law of partial pressures. You just calculate Raoult's law for liquid A, then you calculate it again for liquid B, and simply add those two numbers together to find the grand total pressure inside the container. It's an incredibly elegant way to solve a complex problem. Let's move to and see how this builds in Section 4, Real Solutions and Deviations. This is where the perfect ideal world meets messy reality. So on one hand, we have ideal solutions. For a solution to follow Raoult's law perfectly, the intermolecular forces between the solvent and the solute must be exactly, perfectly equal to the forces between the pure solvent molecules themselves. The molecules essentially can't even tell the difference between their own kind and the new particles. But let's be real, not ideal solutions are way more common. In the real world, adding a totally different chemical introduces differing attractive forces, and that causes a solution's actual vapor pressure to deviate entirely away from our neat little mathematical calculations.
So the crucial point is really understanding the binary difference between the two ways a solution can deviate. First, a positive deviation. This happens when adhesion, meaning the attraction between the different molecules, is actually weaker than cohesion, which is the attraction between the same molecules. The mixed molecules kind of hate each other, so they escape super easily into vapor, making the actual vapor pressure much higher than Raoult predicts. This is an endothermic process, like if you mix ethanol and water. On the flip side, we have negative deviations. This is when the new molecules absolutely love each other. Adhesion is super strong, they hold onto each other tightly, keeping everything trapped in the liquid state, which makes the vapor pressure lower than expected. This is exothermic, like mixing chloroform and acetone.
Because of all these real-world molecular forces, you've got to remember that Raoult's law has some strict limitations. It really only applies accurately to very, very dilute solutions, where solvent molecules are mostly still just surrounded by other solvent molecules. It also completely assumes that no actual chemical reactions are happening between the components. And guys, here is a massive trap to avoid on your exams. The law totally fails if the solute dissociates into ions. If you dissolve 1 mole of table salt in water, it breaks apart. Suddenly you have 1 mole of sodium ions and 1 mole of chloride ions. You actually have 2 moles of particles blocking that liquid surface. If you don't count the actual number of particles formed, your maths will be completely 100% wrong. Let's wrap it up with Section 5, Impact on Colligative Properties. We'll look at how lowering vapor pressure actively changes boiling and freezing points.
Let's connect all the dots we've laid out. A liquid boils when its internal vapor pressure finally grows large enough to equal the atmospheric pressure pushing down on it from the room, right? But if adding a solute lowers that starting vapor pressure, you now have a much larger gap to close to reach that atmospheric pressure. It literally takes more energy, more heat to get that liquid to boil. This is a phenomenon called boiling point elevation. The solution boils at a higher temperature than the pure solvent ever would. And, conversely, all those extra particles disrupt the crystalline lattice structure when the liquid tries to freeze. That causes freezing point depression, meaning the solution needs to get much colder to freeze. We literally see this in action every winter, like when cities dump salt on icy roads so they don't freeze at 0 degrees Celsius.
And this brilliantly illustrates just how sensitive these equations can be in our everyday lives. Think about making a standard fruit drink mix in a big 2-liter pitcher of water. 2 liters of water is over 110 moles of water. If you add in about 1.5 moles of drink powder, the mole fraction of the water remains incredibly high. It's still nearly 0.99. In these super dilute, everyday solutions, the actual vapor pressure drop is incredibly subtle. We're talking maybe just 0.5 millimeter of mercury. But the point is, it is physically real, and thanks to Raoult, it is entirely scientifically calculable.
So, if you take away just one single thing from our time today, let it be this. Molecular interactions at the microscopic level entirely govern the macroscopic thermodynamic properties we observe. By simply understanding how to count particles and grasping their basic attractive forces, you now have the power to link the invisible world of molecules directly to calculable, observable physics. That's practically a superpower.
I'm going to leave you with a bit of a provocative thought to chew on before we go. We've just learned that adding solutes lowers vapor pressure and consequently raises boiling points. But what if you had a massive vat containing a dozen different volatile liquids, and every single one of them had a different vapor pressure? How might chemical engineers use these exact same principles of Raoult's law to selectively boil and separate those specific components in giant industrial refineries? Say, to turn raw crude oil into the gasoline that powers our cars. Well, the answer lies in an ingenious process called fractional distillation,
And Raoult's law is the absolute engine that drives the whole shebang. Keep exploring, stay curious, and I'll catch you in the next explainer.